paper. Thomas Statham. Thomas, is it correct?
That's correct, yes, Thomas.
Okay, so, Thomas. Thomas is a first-year PhD student at the University of Bristol, and the title of his paper is Application of Gridded Population Data, Delineating Urban Area. Please start, Thomas. Thank you.
Okay, great. So today I will be talking about a recent project we've been working on, which involves applying several gridded population datasets with a range of density thresholds to identify urban areas at the global scale. And the purpose of this is to highlight the sensitivity of changing these two terms in the reported urban share. So before defining the problem, I'll quickly explain what we mean by gridded population datasets. So traditionally, population data sources are often represented at the administrative level for visualization and analyzing population distributions over space. As geographers, we are well aware of the boundary problems associated with them, but we're less aware of the temporal problems too. Put simply, census are regularly performed in more developed nations and less for developed ones. So to overcome these spatial problems and sometimes temporal ones, small area estimation techniques are including the likes of aerial interpolation methods, which redistribute population counts at the administrative level to a finer gridded geography. Obviously avoids the boundary issues we discussed earlier, but any uncertainties related to the errors and the spatial resolution represented at the administrative level are reproduced by these gridded population datasets. So one very academic question which bears quite a considerable practical implication is, how urban is the world? So one definition is by world urban prospects and another is by the degree of urbanization. One reports 54% and the other reports 84%. The difference between the two lies in the fact that the world urban prospects defines the country-specific definitions, whereas the degree of urbanization applies a single, globally consistent definition of urban, which are defined independently from the administrative divisions, and this avoids, again, boundary problems. Specifically, the degree of urbanization applies density thresholds and contiguity rules to the GHS pop layer at the 1 kilometer level to define an urban hierarchy. In practice, using one of the other definitions will result in very different planning policies that can be implemented. So if we break this down to the regional scale, we see the larger differences exist in Africa and Asia. And if we then look at the combination of the size and the density thresholds that replicate the nationally defined urban populations, as in the world urban prospects, we can see that only the low density thresholds and settlement sizes reproduce the ones for Europe, etc. Whereas only high density thresholds and settlement sizes reproduce the ones in Africa and Asia. And this is directly related to the fact that Europe, etc., reports both large and medium-sized settlements, whereas Africa and Asia only reports larger ones. And so if we look at the large cities only, defining as having a population count greater than 300,000 people, we can see these differences are very small. And the regional scale differences, we can see in North America and Oceania are the only real places where there's big differences. And this relates to the fact that they report suburbs in their nationally defined urban areas. So we have 3 research problems we have identified here. The first relates to the disagreement in what defines small, medium urban areas in terms of density thresholds. So the degree of urbanization uses a 300 persons per kilometer squared density threshold, but a number of papers have argued this is too low. Therefore, in this study we apply a range of density thresholds ranging from 200 to 4,000 persons per 1 kilometer squared to look at the sensitivity in terms of the reported urban share. Our second issue relates to the uncertainties with the datasets themselves, the gridded population datasets. And so we apply several of them to look at how this also influenced the sensitivity of the reported urban share. And we aggregate this to the 1 kilometre grid cell level again. Our third issue relates to the uncertainties present within the gridded population datasets and how these uncertainties are strongly related to the areas and administrative source units from which they are based. And our analysis so far has focused on 10 low middle income countries across several continents. And finally, so instead of using contiguity-based rules on cells that meet the specific density threshold criteria, we use density-based clustering and specifically the dbScan algorithm. Okay, so spatially, if we apply increasingly high population density thresholds, we get increasingly tighter urban areas, as you can see from this GIF. And then if we break that down into each of the nations, each of the density thresholds, and each of the different data sets, we can look at the reported urban share. So for all data sets, the low-income countries are more sensitive to increasing the density threshold compared to the middle-income ones. And this urban share decreases more linearly for the middle-income ones. Furthermore, these differences between the data sets for each low-income nation is much higher than for the middle-income ones. We attribute this down to the high uncertainties present in the source administrative units from which they're based. And in terms of the sensitivity to change the density threshold, we can see that from depending on the nation studied, this doesn't change an awful lot the reported urban share between 1,000 and 1,600 persons per 1 kilometre squared. Comparing the individual data sets themselves, so the degree of urbanization have actually applied their own approach to the world population dataset, but with that single density threshold. They found that the world pop dataset reports a much larger rural share for all regions, which was most significant within Africa and Asia. By applying our several density thresholds, our findings do support these results up to approximately 600 persons per kilometre squared instead of the 300 persons per kilometre squared. But above this threshold, the world pop actually reports a higher urban share, as you can see. And if we look at the HRSL dataset, which is highlighted in green, this generally reports the highest urban share for the lowest population density thresholds, which relates exactly to the methods it uses, which is a proportional allocation method, which redistributes the population counts to settlement areas. And this has two problems. The first one is the fact that it assumes homogeneity across the settlements, so that doesn't follow true population distributions. And the second lies in the fact that it may include both residential and non-residential based settlements, which is probably why it reports a much higher urban share for the lower density thresholds. And then for the GPU, marked in red, or the gridded population of the world, it is similar to HRSL in the respect that it too assumes homogeneity, and therefore it allocates population counts to areas that do not have population. This includes both rural and urban contexts, which probably explains why the reported urban share is almost always the lowest reported among all the datasets. So what we've shown in this presentation is identifying urban areas using population density thresholds is sensitive to the choice of density thresholds selected, as well as the gridded population datasets. What we haven't shown is whether our approach delineates urban areas with any degree of accuracy and validation, and this was intentional. Population density alone cannot identify urban patterns because cities are complex. Other processes such as interactions should be included to form more hybrid methods. the inherent uncertainties with the gridded population datasets themselves and lack of ground truth data means that validating the different gridded population datasets is a challenge. And so going forward, we plan to first extend our analysis to the global scale and also include, we'll look at the sensitivity in terms of the total population counts as well. And that concludes my presentation.
Thank you, Thomas. It was a nice presentation. Any question? The first question is coming from Melda. Thanks for the great talk. Based on your research, which of these gridded population datasets would you say are likely the most accurate?
That's a complex question because it depends on what type of population distribution you want to model. If you want to look at settlement patterns, then maybe the HRSL. If you want to look at nighttime distributions, then GPW, GHSL, and WorldPop model for that. And then there's obviously other gridded population datasets out there like Landscan, which redistributes population counts for kind of mixed nighttime, daytime populations. So it's really hard to say which. It depends on what your goals are, really. If that answers the question.
Yes, thank you, Thomas. Any other question? Actually, I have a short question. I'm thinking that some of these countries shows a kind of macrocephaly in their urban structure. Do you think this kind of macrocephaly can affect your modeling process and the output? Some cities such as Mexico cities and Bangkok.
Can you repeat that? My connection broke up a little bit.
Oh, sorry. I know some of these countries, especially Mexico and Thailand, show a kind of macrocephaly in the urban structure. I mean, some cities such as Mexico City with a high population, number of population, and Bangkok are like a prime city. Do you think they can act as an outlier?
An outlier in terms of the classification.
Yeah.
Well, I mean, cities obviously form very different structures depending on the urban structure. Some are polycentric, etc. One challenge we have, I guess, is at what boundary in terms of distance do you merge neighboring urban areas which are classified? Because depending on the context, whether it's a coastal city, mountain city, they're all geographically bounded by these certain geographies. So
okay,
it's
yeah, thank you. The next question is, can you clarify what is the driving different shape of the curves? It's from Nick, this question.
Okay. What is driving the differences in the curve? I see.
What is the driving the different shape of the
so
curve?
Essentially, it might be worth me going back to one of the this particular GIF here. So as you increase the density threshold, the proportion of that nation that is classed as urban decreases, and that is based on the total population count. Maybe if this GIF helps in any way, I don't know. Oh, the differences between the curves. I see. At the national scale, it's definitely dependent on the data set chosen. So probably can't see this exactly, but each of the lines represent a different data set, and each of the data sets have different assumptions made, and some of them include different ancillary data sources. So different combinations of those assumptions made, and datasets will redistribute the population count at the administrative level very differently. And that's why you see these different curves. Yep, they're all at the same resolution at the 1 kilometer grid cell level. Initially, a lot of these datasets are available at varying spatial resolutions, but to make it comparable, we aggregated each of the population counts to the same resolution. Is there any more questions? We do plan to eventually release this database once we've published it in a journal and we're happy with it. I mean, it could be useful for exploring further questions, such as the ones related to urban structure, etc., how changing the density threshold results in very different urban forms and structures. But yeah, we're not sure what date that will be made available as of yet. Regarding the question of Danny, so the DB scan itself is really intuitive in this case. So because we're using regular grid cells, DB scan is not sensitive to the spatial irregularity. And what we do essentially is define the minimum distance between each of the cells as being approximately 1 kilometer. Differences in latitude, etc., have made us have to use a specific threshold based on the distance between them. But this is basically clustered on the centroid of each of those cells. And because we've already subsetted all those cells which are urban, classed as urban, we define the minimum number of points as 1 because we want every urban cell classified to be classified as an urban area. Yeah, there's no weights added. Thank you.